Okay, we are live. If there is anybody in the chat section, please let me know if I am audible and visible to you. Just give me a quick thumbs up in the chat sections if everything is fine with my stream, and then we can start our today's session. Okay, thank you. Okay, let's just wait for 2 minutes so that more students will join, and then we'll start our today's session, that is support vector machine. And this is one of the important, and I can say that it is completely based on mathematics. Just understand it carefully, because they can ask you a question at any point of the algorithm of support vector machine. Okay, so let's just wait for 2 more minutes, and then we'll start the session. Okay, so you can see this example. We have given temperature, humidity, and according to that, we are deciding that we are going to play or not. So we have some examples. So if temperature is 85, humidity is 85, we haven't played. And if temperature is 60 and the humidity is 70 on a particular day, then the person has played. And if the temperature is 80, humidity is 90, the person haven't played, right? So that means this is a classification problem. We have to classify that the person is going to play or not according to temperature and humidity. So just think about it, that up to this point we have learned about the algorithm, all the algorithm. Just let me know which algorithm would help me to classify this data if I'll not know about support vector machine. Just let me know in the chat section that which algorithm comes in mind when I'll see this kind of a data. That means I have to classify. So recently, if you remember, we have discussed one algorithm, that is naive Bayes algorithm. What it takes, it takes the value x1, x2, and it would classify that value, right? We have some features and then there would be classification. But if you remember that in naive Bayes classification, at the start, we have taken that all the features are independent. This is one of the assumption we have taken in naive Bayes classification. But here temperature and humidity are not independent of each other, so I cannot use uh, I cannot use the previous algorithm, that is naive Bayes algorithm, right? So that's why I'll use here support vector machine, right? So we'll use support vector machine. Just let me know if any of the student know anything about support vector machine, that what does this algorithm does and how it does. Just let me know in the chat section. Okay, so let's discuss. So what would I do? I'll try to plot this data. So let's plot this data. So we have this data, as you can see that uh, we have temperature and humidity, and these are the points that these black points denote that we are going to play chess. We are going to play, right? 60, 70. We are going to, these black dots represent that the people are going to play chess, and here it is, the people are not going to play chess. So if you remember, we have worked on this kind of data in using logistic regression. So what does logistic regression does? It would basically find out a decision boundary, and it would say that what we have seen in logistic regression, that we'll find out one function hx, that is we'll find out probability y is equals to 1 given x. If hx is greater than 0.5, we'll predict 1. If hx is less than 0.5, we'll predict 0, right? So here I can see that if hx is less than 0.5, that means if the probability of what hx represent, that they are going to play chess, probability that a person is going to play chess. If it is greater than 0.5, so we find out a decision boundary using logistic regression, right? We usually found out but if you would see here that we are not as much confident for the lines which are closer to the decision boundary, right? We are confident, we are not enough confident for the points which are closer to decision boundary, but we are confident enough for those points which are away from the decision boundary, right? Because we know that that if this point is lying here, so I am confident enough that we are going to play chess, right? But if some point is closer to this line, closer to this decision boundary, then I'm not enough confident to say that the person is going to play chess on this particular day, right? So here support vector machine helps us to decide, or I can say that help us to find out this error area, right? So it would help me to find out to do that. So let's see how we are going to work on when I have points closer to my decision boundary, then how I am going to work on that, right? We are going to see that here. Okay, so what would we do? We'll find out first margin. So what is margin? So let's suppose if I'm taking this as a decision boundary, so the closest point this line has, and I'll find out the perpendicular distance, right? This perpendicular distance is known as margin, right? So what is margin? The distance between the closest point. So here I can see that this is the closest point. So this is my margin, right? This is my margin, right? So this point is the closest point to my decision boundary and the point. So I'll say that this is my margin. This distance is margin. But what I have to do, I have to take margin on both the sides. So what would I do? I'll shift this line little bit aside. So what would I do here? Let's say, okay, so we have this line previously. So what would I do? I'll shift this line. Okay, I'll shift this line little bit here, right? Let's suppose I'll shift this line little bit here. So now you can see that the margin here, this margin and this margin, both are equal. These two distances are equal, right? So I'll find out equal distance from the negative points or from the positive points, because I'm taking two classes here. So support vector machine helps us to classify binary classification, do binary classification. So that means you can see that what I have done, I have shifted my decision boundary a little bit, so that I'll get same margin from to the left hand side and to the right hand side, or I can say that same margin from the negative points and from the positive point. And what was margin? The closest distance from the point to the decision boundary, right? So this is a point, and this point, this distance, let's suppose this is a distance, so this is also a distance. So this is my margin. Now the problem here, I'll do here is that I'll find out I have to maximize this margin, right? And I'll find out, let's suppose what I'm doing here, I am saying that this is my region in which I have chances of error, and I have to maximize this width, right? So how do I do that, right? Let me know. Okay, so this is my line, and I have shifted it to the pink line, so that I'll get distance, I'll get margin, equal margin on both the side. That means on the negative points to the decision boundary and the positive points to the decision boundary. So here I can say that I got this as my margin, right? So let's remember this, that this is my margin now. This is I have taken as a margin. Or I can say that decision boundary. Now next thing we have here is this is my boundary, right? And the points which are closer to my decision boundary, I call those points as support vectors, right? Just remember that I call those vectors as my support vectors, which are closer to the decision boundary. Now next thing is that where here we have many decision surfaces possible, right? We have many decision surfaces possible, but we are going to choose those decision surfaces in which we are going to get maximum margin, right? After shifting, that means we are getting equal value, equal distance from the negative points and from the positive point, and I am going to take that margin or that decision boundary, decision surface, which is giving me maximum margin, right? Maximum margin width. I want maximum margin width here, right? So how do I work on this? Let's see, right? So I told you what is support vector. Support vectors are the closest point. Now we'll find out the distance. Let's suppose this xi comma yi is a point on my 2D surface. So I have to find out the perpendicular distance, right? Because I want to find out this margin. So let's suppose I want to find out this distance. Any point distance from this decision boundary, what would be the distance? Anybody knows? So just remember that we call this as a functional margin. We call this as a functional margin. And functional margin is the distance from xi, yi to the decision surface. So if we have a point in my 2D surface, and if I'll find out the distance between that point and the decision surface, that distance is called as functional margin, right? And how do I find out this distance? The formula for finding out this distance is, let's suppose I'm denoting it as gamma I. So this line equation, let's suppose it is wx plus b, this decision boundary, right? Because I'm taking it as a 2D surface, so that's why I'm taking wx plus b. Otherwise, it would get transposed into w vector dot x vector plus b, right? If I do not have 2D vector, right? So let's suppose if we have wx plus b, then what is a normal distance? The formula for normal distance is that yi into w xi plus b, right? This is my distance. Gamma I is equals to wx plus b. But let's suppose this line has a equation. Let's suppose this line has an equation. So here we have this distance as, yeah. So let's suppose we have this line equation as 2x plus y plus 6 equals to 0. Can I write down this equation line as 4x plus 2y plus 12 equals to 0? Right? These two equations represent same line. These two equations represent same line. So that means if I'll use this 2x plus y plus 6 or 4x plus 2y plus 12, this would give me different results. This would give me different functional margin, right? So I cannot use this formula because this formula contains wxi plus b into yi, right? Wxi plus b into yi. But here you can see that if I'll write 2x plus y plus 6, that it would give me another result. And if I'll write down 4x plus 2y plus 12 equals to 0, it would give me different result. If I'll write down 6x plus 3y plus 18 equals to 0, it would give me different result. But equation or all these three equations are same, right? If all these three equations are same but they are giving different results, so what would I do? So what would I do here? I'll normalize this, right? So I'll normalize this formula. So what is the problem with functional margin? I cannot use that to find out a margin distance. So what would I do? I told you that what is the problem with functional margin? So I'll use geometrical margin. What geometrical margin says? Geometrical margin, I'll do y into w dot x plus b, and I'll divide it, I'll normalize this, normalize by w, right? I have normalized this. This is my geometrical margin and I'll represent it with gamma, right? I'm going to use that. So you can see that if you would normalize it, if you would do norm of w, then it would help you. It would always give you same results for different equation. For a single line, we have different equations, so it would give you the same result. So let's suppose if we have 2x plus y plus 6 equals to 0, so that means it gets normalized to 2 square plus 1 square, that means square root of 5. And if I have 4x plus 2y plus 12 equals to 0, if I'll normalize this, what it become? 4 square plus 2 square, right? 4 square plus 2 square. Now in this 2x plus y plus 6 would become 2x plus y plus 6 would become square root of 5 equals to 0. And if I'll say solve this, it would become, let's take 2 common out of it, 2x plus y plus 6 equals to 0, and square root of 4 square plus 2 square, 4 4s are 16, 2 2s are 4, that means square root of 20, and I can take 4 into 5, right? And 4 would become 2 when it would come outside of this from the square root, so it would become 2 square root 5. So 2 square root 5. So you can see that after normalizing, our both the equation would become same. So that's why to find out the distance, to find out this distance, I am going to use functional margin, geometrical margin, right? So now what I have done here, till now, I told you that let's suppose we have some data given to us. and let's suppose we have these points. I have find out a decision surface such that it has some points here and some points here which are of equal distance from the decision boundary, and we call those points as my support vectors. And this decision boundary is at an equal distance from the negative point, from the closest negative point, and from the closest positive point, right? So we have some distance here and we have some distance here, and the problem here is to maximize this distance. And here I have find out that how to find out a distance at this distance from a point decision. Here, what is this geometrical margin? Geometrical margin is a distance, normal distance between a point and a decision boundary, right? That is my geometrical distance. Geometrical distance, let's suppose if we have any point, if I have to find out normal distance from the decision boundary, that is my geometrical margin. And I have normalized that so that it would not give different results for the different equation of a line for a same line, right? Now we got the geometrical margin. Now next thing what I have to do, I have to maximize this width, right? Maximize margin width. So I told you that, okay, yeah. So we have this problem, right? I have this problem. So now can I draw here my, right? This is my margin width. Now I have to increase this margin width, right? I have to maximize this margin width as much as possible for support vector machine, right? Or I can say that I have to find out that decision boundary. I can say that I have to find out that decision boundary such that this distance is maximum. Because these points are not going to change. These points are exactly there. So from support vectors, let's suppose we have negative support vector and we have positive support vectors. I have find out the closest point and I am finding out that decision boundary which maximizes this distance. So how do I find out that that is a problem, right? So what would I do? I have to maximize this gamma. I can say that maximize gamma. Okay. Here problem reduces into that I have to maximize this gamma, right? What would be the condition? Here condition would be that I have to maximize this gamma. Let's suppose this previously we have taken this gamma. Let's take this as gamma upon norm of W, right? Previously because we have used gamma, right? So let's say gamma upon norm of W. I am taking gamma upon norm of W because we have used this notation gamma for the distance, for the functional margin. So I have to maximize gamma upon norm of W. And what is gamma? Gamma is this distance, right? I have to maximize this. Under what condition I have to maximize it? I have to maximize it that such that yi into wxi plus b greater than gamma I, right? It would be greater than gamma for positive points, for positive points, for positive points, and yi into wxi plus b less than gamma for negative points. So now you can see that if we are left of this gamma, if we have this distance less than gamma by I into wxi plus b is less than gamma, that means we are reaching this point. So these are negative points. If we have yi into wxi plus b greater than gamma, then we are having positive points, right? So if this distance is greater than gamma, then we have positive points. If this distance is less than gamma, then we have negative points. We have to under this condition we have to maximize gamma upon norm of W, right? So this distance gamma we have taken by ourselves. So this gamma distance you can take it as 1, right? I can take this gamma as 1. We can scale so that gamma would become 1, right? I can scale this diagram so that gamma would become 1, right? So if gamma would become 1, so my problem would get converted into this one. So basically I am taking this value as 1 and this value as 1. So I have to find out this decision boundary such that I got this maximum value of 1 by norm of W and this condition. Right? I have to find out this. So can I say that? Can I say this instead of that? Can I say that we have to minimize W comma B such that so we have previously we have the problem that is maximize 1 by norm of W, right? So this maximize 1 upon norm of W, can I write down this as minimize norm of W? And it does not make any impact if I'll take a square of it. And I'm taking half of it. Why I'm taking half? Because it would help me in differentiation. Right? So to find out maximize of 1 by norm of W is same as minimizing of norm of W. And I am taking square. So if we have a distance, square root and all those get cancelled. And because of derivative, I am dividing it by 2. Right? So if I'll divide it by 2, I got this. Now, my problem gets converted into, okay. Now my problem gets converted into that we have to minimize 1 by 2 norm of W square subject to yi into W transpose xi plus b minus 1 greater than equal to 0 for I varying from 1 to n. Right? So my problem gets converted into this. Right? Now, because we reach to this problem, now how I can find out the solution for this problem? How we can find out the solution for this problem? That's we have to use duality and all Lagrange method. So I don't think that is required to find out the solution for that in detail. You just remember that the solution for this problem would be, so in this problem you can see that what you have to find out, you have to find out W, right? You have to find out W and B to find out a decision surface because its equation is Wx plus B. So that means you have to find out W and B to get that decision boundary in support vector machine, right? You have to find out W and B. So how do you find out these W and B? How do you find out that? So the formula to find out W and B is alpha yi xi vector, alpha yi and xi vector, and that is sum of all these values. That would be W, and B is minimum I dot yi plus 1 when this is plus 1, W vector dot xi, maximum I comma yi minus 1 equals to minus 1, then W dot xi. So we have to take minimum and maximum of those values. And what is alpha here? Okay, okay, I think there's some problem. Yeah, okay, just a minute. Yeah. So we have the solution, which is W is this and B is this. You would understand once we solve one question. If it is confusing to you that how do we get this, I'll tell you using an example. So this is my, how do I find out this alpha vector? So you can see that in this W, I know yi, I know xi. I know xi, and once I get W, I can use it here, right? I know xi. But one thing I do not know, that is alpha I. So how do I find out this alpha vector? Alpha vector is basically summation I varying from 1 to n alpha I minus 1 to 1 by 2, I varying from 1 and j varying from 1 to n. And we have this alpha I, alpha j, yi, yj into xi dot xj vector, right? And summation such that alpha I yi is 0. So that means we have to maximize this vector such that alpha I yi is 0, right? So let's understand this problem. I know it's really confusing, but let's see how we are going to solve that, right? So what it is saying that we have to find out vector W and B such that and we get alpha from here. So just let's take alpha. What is alpha? Summation I vary from 1 to n alpha I minus 1 by 2 summation I varying from 1, j varying from 1 to n. We have to maximize this to find out alpha. Alpha I, alpha j, yi, yj, yi, yj, and xi vector dot xj vector. because there may be a possibility that it's a 2D vector or 3D vector. So I have to find it accordingly. So I have to maximize subject to summation I varying from 1 to n alpha I yi equals to 0. I have to maximize this to find out alpha. So let's see how we are going to find out the value of alpha. So here, let's suppose we have this given problem and they are saying that using the SVM algorithm, find the SVM classifier. I have to find out the SVM classifier. So I know that I have to find out the values for W and B. And for W, I have seen that I have to find out the alpha value in the solution. And alpha value I find out using this summation alpha I. So I can see that I have 2 points, x1 and x2, and it gets classified as 1. So, and how many examples we have? I have 2 examples. So that means my alpha vector would be alpha 1 comma alpha 2, right? This is my alpha. So that let's take summation alpha, that means alpha 1 plus alpha 2 minus 1 by 2, and summation I equals to j equals to n alpha I alpha j. So let's say, let's do this. So alpha 1 y1, let's take I equals to 1, j equals to 1, because it is varying from I1 to 2 and j1 to 2 it is varying. So I can take these values, alpha 1 by 1, let's take I is equals to 1, j is equals to 1 in the first case. So we'll get x1 x1 x1, right? We got this point. Now let's take alpha I1 j2. So we'll get alpha 1 alpha 2 y1 y2 and x1 x2. Next take I2 j1. So we'll get alpha 2 alpha 1 y2 y1 and x2 x1. Next take both 2, alpha 2 y2 y2 and x2 x2, right? We have this data. Now I have all the values of x1 y1 and I have all the values of x1 y1 and x2 y2. So let's put the values. So what is x1 y1? So I have find out alpha 1 corresponding to that, alpha 2 corresponding to that. So this is x1, this is x2, sorry. So let's find out x1 dot x1. So these are the vectors, x1 dot x1 and x1 dot x2 and x2 dot x1 and x2 dot x2. I know that it's very complicated. So let's take this as x1 vector and let's take this as x2 vector. Now solve. Alpha 1 plus alpha 2 minus 1 by 2 alpha 1 square y1 into y1. That means 1 square. That would give me 1. And what would be x1 dot x1? Just let me know what would be x1 dot x1. Just try to solve it. So alpha 1 would become alpha square, y1 is 1. So it would become 1 into 1, that is 1 square, and x1 dot x1. That means I have to multiply 2 comma 1 dot 2 comma 1. So it would become 2 2s are 4 plus 1. That would become 5. Right? Alpha 1, alpha 2. Let's write it as it is. Y1, y2, 1 into minus 1 would become minus 1. And x2 dot x1. x2 is 4 comma 3. Dot x1 is 2 comma 1. So it would become 4 2s are 8, 3 1s are 1. So 8, 9, 10, 11. So it would become 11, and this term would become y2 into y1 and alpha 2 alpha 1 and x2 x1. So it would become alpha 1 alpha 2 minus 1, and x1 dot x2 vector multiplication is dot vector dot product is commutative. So we'll get the same result as we get here, 11. Right? Now alpha 2 my alpha 2 square plus y2 into y2, that would become 1 because it is minus 1 here, and 4 dot 3, and I have to multiply get the dot product, 4 dot 3 dot 4 dot comma 3, that would become 16 plus 9, that means 25. So we get this value as 25. So on solving, what would I get from here? Alpha 1 plus alpha 2, right? What you get, just solve it and let me know what would be the value here. So can I write down here that this would be minus 1 by 2 5 alpha 1 square and this would become minus 11, minus 21, 22 alpha 1 alpha 2 plus 25 alpha 2 square. We got this, right? This is what, this is my support vector. This I have to maximize. I have to maximize this function. Let's take it as z. I have to maximize this z subject to alpha yi 0. So alpha yi would be alpha 1 minus alpha 2 0. I have to solve this maximize of z such that alpha 1 minus alpha 2 0. And how would you solve it? How would you solve it? So you can find out that from here that alpha 1 equals to alpha 2. So I can substitute this value. So z would get little converted. So let's convert it into one variable. So z would become, let's put here alpha 1. So I am taking alpha 1 alpha 2 equals to alpha. So it would become alpha plus alpha minus 1 by 2, and it would become 5 alpha square minus 22 alpha square plus 25 alpha square. So it would become 2 alpha, and it would become 25 plus 5, 30 minus 22. 30 minus 22 gives me 8 alpha square. That means minus 4 alpha square. So this is my z. I have to maximize it. So to maximize any function, what would I do? I'll take the derivative dz by d alpha. It would become 2 minus 8. Okay, we have in division 2 as well. Right, I forgot that. So we have 2 here. So I'll get here alpha minus 2 alpha square. Okay, let's. So we get this here alpha minus 2 alpha square. We get this derivative. So I'll differentiate now. It would become 1 minus 4 alpha equals to 0. Alpha would become 1 by 4. Right, so alpha is 1 by 4. So that means alpha 1 equals to 1 by 4 and alpha 2 equals to 1 by 4. So let me know, guys, if anybody doesn't get it, how to find out alpha 1 and alpha 2. Just let me know, because the next thing is just putting the values. You just have to put down or write down all the values of alpha 1, alpha 2 in the problem. Just let me know, guys. So we get from here the values of alpha 1 is 1 by 4 and alpha 2 is 1 by 4. So alpha 1 is 1 by 4 and alpha 2 is 1 by 4. Right, now the problem here reduced to that I have to find out w and b. So I'm writing here that w is basically summation I varying from 1 to n alpha I, yi and xi vector, right? And b gets reduced to 1 by 2 minimum I dot y I equals to plus 1 w vector dot xi vector plus maximum of w vector dot xi vector I dot yi equals to minus 1. I have to find out these w and b. These two values are equal. Alpha 1 and alpha 2 are equal. So that's why they would always be 1 by 4. Okay, you are telling me z and b minus 1 by 2 and 1 by 4. Okay, so let's find out what is w vector. So if you are telling me w vector is what? Summation alpha I, yi, xi vector. Right? So it would become alpha 1, y1, x1 vector, alpha 2, y2, x2 vector. So alpha 1 is 1 by 4, y1 is 1, and x1 vector is 2 comma 1. Right? This is x1 vector, this is x1 vector, and this is x2 vector. And 1 by 4 into 1 into minus 1, because y2 is minus 1 and x2 vector is 4 comma 3. So if I'll solve this, it would become 2 by 4 comma 1 by 4 vector plus minus 4 by 4 minus 3 by 4 vector. Now if I'll solve this, 2 minus 4, that means minus 2 by 4, and 1 minus 3 by 4, that is minus 2 by 4. So we get this as minus 1 by 2 comma minus 1 by 2. So that is my w vector. Right, so let me know if okay, you were telling me alpha, but alpha I got as 1 by 4 comma 1 by 4, because we have seen that na alpha 1 and alpha 2 are equal. We have seen that na alpha 1 and alpha 2 are equal. Just check the calculation one because I got both values 1 by 4, 1 by 4. Right? Here I got this W vector that is minus 1 by 2, comma, minus 1 by 2. Now try to find out the value of B here. Sorry, I mean 1 by 2 and minus 1 by 2. Okay, W vector is minus 1 by 2 and minus 1 by 2. That is W, right? Now let's find out B. So B says that minimum of W comma Xi when we have Yi is 1. So Yi is plus 1 only in one class. So we do not have to take minimum because it is always a minimum. So 1 by 2, that would be, I can write down here, W vector. W vector is, let's put all the values. So I'm just writing W vector dot X1 vector plus maximum of when I have I dot Y1 is negative. So we have only one value which is negative. So I do not have to consider this maximum because this would always be maximum because we have only one value. So I'll write down W vector dot X2 vector. X2 vector. Now let's find out the value. 1 by 2. W vector is what? Minus 1 by 2 comma minus 1 by 2 dot X1. X1 is 2 comma 1. Plus I have to take a dot product. Minus 1 by 2 comma 1 by 2 and X2 vector, that is 4 comma 3. Now let's solve it. So how would I solve it? So we have 1 by 2 outside. So minus 1 by 2. So it would become, let's solve minus 2 by 2 and minus 1 by 2. That would become minus 3 by 2. Minus 2 by 2 and plus sign, with plus sign. So, right? Now we have to multiply this. Minus 4 minus 3. That would be minus 7 by 2. So it would become minus 10 by 2. That means minus 5. Minus 5 by 2. So the value of B is minus 5 by 2. So just check the values that if you are getting these values or not. Just let me know. Just try to solve this once and you would get to know how to work on this method, right? So you just have to remember for support vector machine that what is the solution and what problem you have to solve. Just let me know first if you have problem in this. We'll discuss that and I'll tell you that what you have to remember for support vector machine. I'll give you a quick summary of this algorithm support vector machine. Okay, so in support vector machine, what we are doing, let's see at the start. So what we have done, we have some points given, we have some classification. I have to find out decision boundary such that I have uh, I have maximum margin width. And why it is that? Because I know that when points are closer to decision boundary, I'm not enough confident. So I want my decision boundary as much far away from all those points given to me. So what would I do? First, I'll take a closest point from both the sides. If it is closest to this point, let's suppose if I'm taking this down decision boundary, I'm getting this distance as closest. So I'll move it little bit to the right so that I'll get both the points here which are closer to decision boundary. That positive points and negative points are of equal distance from the decision boundary. Now I want to maximize this distance. I have to find out decision boundary such that this decision gets maximized. So I have converted this problem into this minimization problem. Right? To solve this problem, what I have to do, I have to find out the solution using this method. This is a formula for W, this is a formula for B, and in this formula you can see that all yi xi are given to me in examples. This alpha I have to find out using this formula. Right, using this formula, that means I have to maximize this equation such that we have given this condition as well. So if I'll go through this, I'll get alpha, and using the alpha xi yi value, I can find out W and B. That is my solution, right? That we are doing in support vector machine, right? This is a main numerical problem. Now just let me know what would be the solution for this problem, right? This is one of the question we have made. It says that suppose you are using a linear support vector machine classifier. Linear means that we are using a line, right? Because we have a two class classification problem and we have 2D data points. Consider the following data in which the point circle red represents support vector. Will the decision boundary change if any of the red points are removed? So let me know. So we have discussed support vector machine. Just let me know that will the decision boundary change if any of the red points are removed? You can see that. Let's suppose if all these 3 points are my support vector, then I have this decision boundary here, right? This would be my decision boundary because now these distances are equal, right? And this is closest. But let's suppose I'll remove this point. Then what would be my decision boundary? Then my decision boundary would become this. Then I'll have a equal distance from this point and this point, right? Then there is no point of taking this as my decision boundary, right? So I'll take this as my decision boundary if I have only 2 points, right? So yes, decision boundary change if any of the red points are removed. So support all the support vectors are important if we are finding out decision boundary, right? Now just let me consider the data points in the figure below. So you can see this is the figure given to me. Let us assume that the black colored circle represent positive class. So these black colored circle represent positive class and white colored circle represent negative class. So this represent negative class. And then we have which of the following among H1, H2, H3 is maximum margin hyperplane. So tell me which out of this H1, that is green, blue and red, H1, H2 and H3, which is the maximize hyperplane, right? Which is the okay maximum margin hyperplane. Let me know in the chat section, guys, which is maximum margin hyperplane. So you can see by yourself. Just let me know which is maximum margin hyperplane. Let me know, guys, which is maximum margin hyperplane here. HE. Okay. Right, Avi. So yeah, you can see that if I'll talk about H2, H1 is not a hyperplane because it is not classifying, right? So H1 does not work here. So I'll not take H1 into consideration. But if I'll see H2 and if I'll compare H2 and H3, the distance H2 is having with these points is this much only, right? But if I'll talk about H3, this is a distance, this is a distance. So I can say that H3 is my maximum margin hyperplane. So option C is correct, maximum margin hyperplane. So you can see that the question which we have discussed in detail, the mathematics, there might be a possibility they would ask and they would ask a little part of it, but these type of questions they can surely ask. So just understand the concept behind support vector machine. So soft margin support vector machine is more preferred than hard margin support vector machine. So what is soft margin and hard margin? Does anybody knows? So when we have a noisy data, then we'll take a soft margin, and if we do not have a if we do not have noisy data, then we'll take hard margin. So that means that if we have in this, let's suppose if we have any of the error, let's suppose if we are having one error here and we have some noisy data and we have one point here, so I'll classify this, but we have some errors. That means we cannot use hard margin here, right? Hard margin means that I'll exactly classify, right? So there may be chances of some error, then we'll take hard margin, otherwise we'll take soft margin. So soft margin is more preferred when the data is linearly separable. Sorry, when the data contains overlapping points. So soft margin, we'll take hard margin when the data is not noisy, right? We can classify the data linearly, then we'll take hard margin. If we are not able to classify the data linearly, we'll use soft margin. Right? Okay, so just go through this once. Okay, we have one more question, that after training in SVM, we discard all examples which are not support vector. Can still classify new examples true and false? Just let me know this question answer. Let me know the answer of this question. After training an SVM, we can discard all examples which are not support vectors. So just remember, if you have trained, so we in only training we use support vectors. There is no need of support vectors after this. If once I have find out wx plus b, if I have find out w and b, then there is no need to find out support vectors. There is no need of support vectors. What would I do? I'll take the point x and I'll fill in this my decision boundary. If wx plus b is greater than 1, I'll classify it as positive. If wx plus b is less than less than is less than minus 1 or is equals to minus 1, then I'll classify as negative points, right? So yeah, we can classify right away. We can classify because support vectors only required for us to get a decision boundary, right? Later on it is not required. Okay, so just go through this once and I'll discuss if you have if you have any problem in the next session, right? And if you have any doubt, just let me know right now as well, and then we are going to discuss further in the next session. Just let me know, guys, if there is any question in support vector machine. Just go through one more problem for support vector machine. Should I tell you the problem or you would take by yourself? Okay, so I am sharing it, but it is little bit lengthy. So just try to solve it. If you would not get it, then I'll try. I'll let you know. So I'm writing it here. The problem. So it is the problem in which you have to solve it completely. So we have this x1, x2. Basically, let me not write down x1, x2 because it would uh, so these are the features, and this is x1, x2, x3 vector. These are the vectors and these are features f1 and f2 that I am writing, so that you would not get confused that what are the values I have used in the formula and the problem, right? So we have the example 1, 2, 3. Now previously we have solved that we have three vectors, two vectors given. Now if I have three vectors given, I know the problem gets little bit lengthy, but it would make you remember all the concept. 4 5 7 4, and y would classify as -1 +1 +1, right? -1. Yeah, this is a problem. So this is a feature. So we have three example given. So x1, x2, x3 would be that. x1 vector, x2 vector, x3 vector. Okay, so just try to solve it and we'll continue in the next class. Okay, so that's all from my side. Thank you, guys. Thank you for joining.